etc. In J1, J2, J3, etc. Jm. So this is a tensor of n plus n rank. Okay, so rank of this tensor is m plus n. Rank is m plus n. Now supposing if I make any of these indices equal, one index on the superscript and other index on the subscript, if I make them equal, then what happens? So suppose, say, I2 is equal to J2. So that means I have Ti1, I2, I3, etc., In, and J1, I2, J3, etc., Jm. One superscript and one subscript are same index. That means what? You have to sum over that index. When you sum over that index, what happens? This implies this is sum over I2 over whatever is the number of components that you have. I1, I2, I3, etc., In, J1, I2, J3, etc., Jm. So when you sum it over, these two indices are gone. Correct? These two indices are not there. That means essentially you have, this is equal to T. What are the free indices? Free indices are only I1, I3, In, you can write down I1, I2, In minus 1, J1, J2, Jm minus 1. So the rank of a tensor when you contract will come down by 2. If you have a rank M matrix, a rank M tensor, when you contract the rank M tensor, then you will get a rank M minus 2 tensor. The rank upon contraction reduces the rank. So this is one operation by which you can increase the rank of the tensor. Sorry, decrease the rank of the tensor. This is called contraction.
So how do you finally write the contracted version? Contracted version, how do you write? So I1, I2 are gone inside.
Yeah, I1, I2 are summed over.
I2 is gone.
I2 and here J2 is same as I2.
So here, I1, I3 is.
Yeah, so if I write I3, I will write up to n. But these are any free indices, so I can simply write as n minus 1.
So what is the physical meaning of such a number?
Physical meaning of such an operation, it depends on kind of the physical quantity that we are talking about. As such, if I define a contraction of a tensor, it only has a mathematical meaning. But if I have a physical object which is represented by the tensor, then contraction operation can be viewed as defining the corresponding lower order tensors. For example, if I have a third rank tensor, maybe I can have a corresponding vector by means of a contraction. So this operation will allow us to map lower order tensors to higher order tensors.
Also, sir,
Yeah.
in earlier classes, I learned moment of inertia is like one scalar. Then they say it's a tensor.
Yeah.
Practically, how do you understand?
Well, the moment of inertia, it is exactly like what we have talked in the previous example. The susceptibility, if your material is isotropic, then the susceptibility is a scalar. First, we have talked about susceptibility as what is called a multiplier of the identity matrix. So when you say moment of inertia is a scalar, it means it is a multiplier of a identity matrix. But you can have a situation where moment of inertia is not. See, essentially, when angular velocity is not in the same direction of angular momentum, the moment of inertia has to be a tensor quantity. Okay, so you can you can write down angular momentum vector as, if you have a set of particles, I is equal to 1 to n number of particles are there, then Ri cross En. These are the angular momenta, and you can write down this one as I is equal to 1 to n Ri cross Pi. You can write it as mass of each particle into Vi. But if something is rotating about an angular velocity, then your Vi can be written as omega cross Ri. If all this system of particles is rotating about an angular velocity, then you have this one to be sum over I is equal to 1 to n mi Ri cross omega cross Ri. Now it is very easy to.
So this is for a rigid body.
This is for a system of particles.
Rigid body,
Not necessarily rigid body.
Omega.
Omega is a constant angular velocity
For all the particles.
for all the particles, for the system of particles. Now you can say that this you can expand using this vector identity. This can be written as sum over I is equal to 1 to n mi into, you can use that rule, A cross B cross C is B times A cross A dot C minus C times A dot B. So you can write, so this is omega times R square minus Ri square minus Ri times omega dot R. Now exactly like in the previous case, we expand this one. So you try to write this as a matrix, and omega x, omega y, omega z. This will be equal to Lx, Ly, Lz. When you write it like this, you will see that you will get a matrix where this is Ixx, this is Ixy, this is Ixz, Iyx, Iyy, Iyz, and Izx, Izy, Izz. And if I write x as x1, y as x2, and z as x3, then I have Ijj will be sum over I mi into x. This I is over all the particles. Okay, so xjj is, okay, so let me put it this way. I will generally write it as any I comma j is equal to R square delta ij minus xi xj. Okay, so maybe I should use slightly different notation here. Mi, now let me call this as jk or alpha beta, that is better. So alpha beta mi into ri the square into delta alpha beta minus x alpha x beta xi alpha. This is for the ith, not know how to write, xi of alpha and xi of beta. So that means this is ith particle, this is the particle index, this is the component of the vector. So you can get the I alpha beta components like this. So I think we will do a problem tomorrow how to calculate this moment of inertia tensor. And usually if you have a rigid body dynamics, you take any particular coordinate system, calculate the moment of inertia tensor, and then you can actually diagonalize the moment of inertia tensor, find out the eigenvectors of moment of inertia tensor, and those directions corresponding to the eigenvectors, they are called principal directions or body set of axes. Body axis, from a space axis to body axis, you can go by diagonalizing moment of inertia tensor. And eigenvalues of moment of inertia tensor are called principal moments of inertia tensor. So, any dynamics, the problem in classical rigid body dynamics is simple. It can be simplest if you work in the body set of axis. Now, how to choose body set of axis? Choose any set of axis. Find out the moment of inertia tensor. Diagonalize the moment of inertia tensor. Find out the eigenvectors of moment of inertia. They are the body set of axis for the rigid body that we are working. Okay? You may see, I think in classical mechanics, one problem which is there in the syllabus of every university is symmetrical top problem. Symmetrical top problem does not have any translated motion, only rotational motion. And you can see body set of axis corresponds to those directions correspond to three different Eilerian angles of the problem. So this is about the moment of inertia tensor. Okay, I will just define one last quantity, which is, I'm not going to discuss details, but maybe it is required if you are studying general relativity sometime. So that is this is called the covariant derivative. Covariant derivative. Essentially, this is defined as gradient of a vector. Normally, we know that gradient is defined for a scalar, right? But this is gradient of a vector. Supposing if you have a vector with the components a nu, e nu like this, and you want to define a gradient of this quantity, then you can write down so this gradient is a one form like this. So this is E mu into del mu A mu A that is del can be written in this fashion. So this can be written as del mu A nu into E mu A nu plus A nu mu into del mu E. Essentially, it is like saying this gradient operator will act on this way, and it will also act on this, because your basis vectors also will depend upon the coordinate at which you are choosing. As we said, there is a a basis vector can be chosen at a particular coordinate. So this one, normally you will have only this term, but here we have an additional term. Now this particular quantity can be defined as at a particular, so at a point x, you can say dou mu of E mu. This will be written as gamma mu nu. These are two symbols that are here, mu nu, free indices, into a lambda, into E lambda, E lambda. That means whatever vector that comes out here can always be represented as a linear combination of the same basis. Okay, so these possible coefficients, which are this set of coefficients, are called Christopher symbols. So these coefficients are Christopher symbols. So the covariant derivative del mu a mu can be defined as del mu a mu defined as del mu a mu plus gamma mu of mu lambda into a lambda. So it is exactly like this. I have a lambda pulled out, and this one is written in terms of a mu, and everywhere this quantity is there, so we can know that. So covariant derivatives, or the gradient, can be always written in terms of these things called Christopher symbols. And these are used when we have tensor fields and take derivatives of the vector quantities. So I thought I will just introduce this, and since as a name, define it, and then leave it at that.